Fine. Okay, I think Asmita is not disconnected. Fine. So we'll start the lecture. So welcome to lecture number 15. And then today we'll see the remaining part of texture and color. In the last lecture, we have started about how to extract the textural features. So in that particularly, we talked about what is texture, what are different types of textures, and then how texture analysis is done. So that part we have done. And we have seen that, okay, there are three ways of doing the texture analysis. One is particularly based on the local approach, and another one is global approach, and then third one is basically spatial relation, or this one, okay, geometrical approach, and so on. So like that way we have studied in our lecture. Now we'll see here. Also we have studied about the one method last time. We'll start the basic. Okay, we'll start the next part, that is statistical based approach for texture description. So in statistical based approach for texture description, there are various approaches, like for example, age density and direction is one of the method for extracting the textural features, or LBP. It is called as the LBP, that is local binary pattern. Okay. It is also a very good effective technique for extracting the textural features in basically in most of the applications this LBP method is used. And then histograms and features also. So from the histogram, local histogram, you can extract the features, several moments you can extract, and then you can find the feature. Then co-occurrence matrices and features we can extract from the texture, and then autocorrelation and power spectrum. So these are basically the textural features based on the statistical approach. And then spectral approach or global approach, like as I told you that basically in statistical approach, you are considering the small portion of the image. You are extracting the features from that small portion. So it is called the local approach. Whereas global approach or spectral approach, you are considering the entire image. You are taking the transform of that one, maybe Gabor transform or Wavelet transform or Laplacian Gaussian, and so on. And after that, you are extracting the features from the transform domain. So that is nothing but the global approach. So in this lecture, we'll try to study this statistical approach as well as global approach. So first we'll study how to estimate the edge density and direction features. Then we'll study how to extract the LBP patterns from the image. Then how to extract the histogram features of textured image. Then how to find co-occurrence matrices, and then features from that co-occurrence matrices, and then autocorrelation and power spectrum, and so on. So first one is basically age detection, which is age density and direction. So age detection is simple and easy to apply. Already we have studied in our second chapter how to detect the ages. So we have to continue that one and then apply it to the textured image. So to detect the ages of the texture image, and then after that, the number of age pixels in a given fixed size region gives some indication of the busyness of that region. So if more number of edges are there, so that region will be more busy. If less number of edges are there, that that region will be less busy, and so also like that way. And you know that when you are extracting the textural this one edge features, so you have edge direction as well as edge magnitude. So you get the direction as well as you get the magnitude. So the direction of the edges also describe the characteristic of texture pattern. So from this edge, we have to describe the textural patterns. So how to do that one? So once you have extracted the edge features by using various edge operators, then you will get the two things. One is magnitude of the edge, and you'll get the gradient, that is the direction of the edge. So you have to calculate on the local region, you have to calculate the gradient of the magnitude and the gradient of the direction. So you have to calculate that one. And then from that, you can calculate the edgeness per unit area, that is EPUA. So this edgeness per unit area, this measures the busyness but not the orientation of the texture. So what they are doing here, how to calculate the edgeness? So F edgeness is given by the magnitude of this one P. Area is nothing but the P. Then if this magnitude of P is greater than the threshold value, okay, and then divided by the number of pixels you are considering in that region. So from that you can calculate the F edgeness there. Okay, so how we are doing, basically from magnitude of that edge pixel, and then which is greater than some threshold, you have to decide the threshold value, and then this is total number of pixels you are considering. So EPUA measures the busyness but not the orientation of the texture, and then this is extended to both busyness and orientation, that is edge density and direction. Okay, so let, for example, H magnitude R denotes the normalized histogram of the gradient magnitude of the region R. Okay, and then H direction R denotes the normalized histogram of gradient orientation of the region. See, earlier in this we have considered, in busyness we have considered only this one magnitude, and this does not talk about the orientation. So edge density, this one edginess, edginess of the texture you can calculate by this formula, and then this can be extended for busyness as well as orientation, so in edge density and direction. So in that you have two histogram. One is basically H magnitude R, okay, of that region. R means that region, okay, denotes the normalized histogram, H per histogram of gradient magnitude of region R. Means you have to decide the region. It's a local, this one, you are doing operation on the spatial domain. So you have to consider the region, that small region, and in that, what is the histogram of that gradient magnitude? So you have to plot the histogram of that gradient magnitude, and what is that one? Basically normalized. Now you know that normalized, how to do the normalization. By using the normalization technique, you have to arrange that one between 0 to 1 range, and then you have to plot that H magnitude R region, right? Then let H direction R denotes the normalized histogram of gradient orientation of this region. Means you are finding the H magnitude R and H direction R, that is normalized histogram of H magnitude and normalized histogram of gradient orientation separately of that particular region R. Then the quantitative texture description, see, this is obtained from the edge of the image, like magnitude histogram and direction histogram, and then from that you are going to extract the textural features. How to extract the textural feature? The quantitative texture description of region R is given by F magnitude and direction. So this value, whatever you get, this one, and then direction, H direction of region R. So you get the textural features like as H magnitude and direction. And then when you are comparing the two textures, okay, of this one based on the edge density and direction, so what you have to do basically, L1, you have to use the L1 distance. L1 distance is simple distance, L2 distance is your basically Euclidean distance, and so on. So L1 distance we can call as the Manhattan distance also, which is nothing but, see that H1 is the suppose for example histogram 1 and H2 is some histogram 2. So how to find out the distance between H1 and H2? So just you have to take the difference of that ith element of H1. Okay, it means you have to subtract the ith element of H2 from ith element of H1, and then you have to do the summation of that one. See, so definitely if both are same, definitely this H1i and H2i are same, then this difference will be equal to 0. But if it is different, then this, okay, will be non-zero value, and then you have to do it for all those value of I from ranging from 1 to n. So this n, small n, is nothing but the number of basically pixels you are going to consider in that region, right? So in that way. Now second feature you can extract from this one of textural features. Just one minute. And that is a well-known local binary partition, okay, LBP. So how you are doing, like for example, you have considered a 3 by 3 image, local, Okay, so you are considering the 3 by 3 image. Like for example, out of you have image size like as a 512 by 512, and then you are finding the LBP pattern of that 512 by 512. So in that you are considering only the region of 3 by 3. So like top, you are scanning from top left to right bottom. So you have considered only a 3 by 3 region, and then for every pixel you are finding the LBP pattern. So how to find the LBP pattern? For each pixel P, see this is the pixel under consideration P in the image, create an 8-bit number like B is equal to B0, B1, B2, B3, B4, B5, B6, B7. Now how to create this B0 to B7? See that for this pixel, which are the neighboring pixel, like as this is, we can consider this as a first neighboring pixel, second neighboring pixel, or 0th neighboring pixel we can consider. Okay, we can correlate that one with B0, then this as a B1, then this as a B2, and then this as a B3, then B4, B5, B6, and B7. Okay, so in the image you have all those gray level values, but you have to obtain basically a local binary pattern. Means your value corresponding here will be of 8 bits. See that how many bits are there? B0 to B7. Now this pixel will be replaced with a 8-bit pattern. Now what will be the B0 value? So B0 value, see in binary you know that either that value will be 0 or 1. Now how this value will be decided, whether B0 will be 0 or 1? So you have to compare this pixel intensity with this one. Now when you are considering B0, so compare this one pixel under consideration, that is P pixel, and intensity of this one. If intensity, this is I, suppose I is this one, okay, and IP is this one. So if II is greater than IP, then this will be assigned B1, BI will be assigned as a 1. Like for example here it is a 5, right? So this, if P is having intensity equal to 5 and then this is 0, so whether this is greater than this one? No, because P value, intensity of P value is greater than this one, so this B0 will be equal to 0. Got it? Now, okay, another thing is that if it is 5, then what about this B1? So 5 is greater than 1, so this B1 will be also 0. Then what about this one? It will be 0. What about this one? It will be 0. What about this one? It will be 0. What about this one? So it is equal. It is not this one greater than. So it will be again 0. But from this one and this one, so B6 and B7 will be 1, 1. Right? So we'll see one example. In my next slide, I have given that one. So in that way, you can calculate the local binary pattern for every pixel, and then that local binary pattern you can use as a texture features for this one. So texture is represented by the histogram of P, that this histogram, right? Then L1 distance can be used to compare the two images of two different texture images, and so on. Right? Now, suppose for example, you have this image. What is the size of this image? See that how many rows are there? 1, 2, 3, 4, 5. 5 rows are there. And how many columns are there? 1, 2, 3, 4, and 5 columns are there. Now we'd like to find out the local binary pattern of this image. So first we are going to consider the 3 by 3. Right? So what is the center one? This is center one, right? Now, how we are going to find out the local binary pattern? See, it is 8-bit pattern. How it is found? So you have considered this pixel under consideration. So this will correspond to this one. Now, we are going to find out the values of this B0. So what is B0 now here? You are considering this 147. 147 is greater than 110. So if it is greater, see that if this value is greater or if this value is smaller than this one, then this pattern will be equal to 0. So 110 is less than 147. So this is 0. Now what about this one? So this is, suppose for example, 200 value is there. Suppose this is 200. 200 is greater than 147. So if this is greater than 147, then this value will be B1 will be equal to 1. Again 198. So 198 is greater than 147. So this will be equal to 1. Now this one, we are coming here. Okay. So 110, which is greater than 147, less than 147. So this will be equal to 0. Right? Again 137, which is less than this one, which will be equal to 0. Now 47, which is less than 147, so it will be equal to 0. 89, which is less than this 147, so which will be equal to 0 here. And then 56, okay, so it will be less than this one, so it will be 0. So local binary pattern of the pixel under consideration, this pixel under consideration, after calculating the local binary pattern, you will get the binary pattern like this. Now when you are considering this pixel under consideration, so you have to shift this window to the right by this one. So 137 will be at the center, and then this 200, 198 and 30. So this region will be considered to calculate the local binary pattern of 137. So what will be this one? 137 and 200. So it will be 200 is greater than 137, so it will be 1. 198 is greater than 137, so it will be 1. Then 30 is less than 137, so it will be 0. I hope that you have understood how to calculate. So you can calculate the local binary pattern for every pixel, then your local binary pattern image will be basically like this. Then you can use this one for comparing the two images. You can use element distance for measuring the similarity of this histogram, right? So in this way LBP is calculated, right? Now histograms, okay, you can obtain the histogram of the image and this one texture image, and from that histogram you can extract the features. So you know that how to extract, okay, how to what is histogram? Histogram is nothing but the plot top pixel intensity values or number of occurrences. Like for example, if you are considering simple gray label image whose intensity is varying from 0 to 255, so how many pixels are there of 0 value in the entire image? Suppose for example in 256 by 256 there are 100 pixels having 0 value, so count will be equal to 100. Then one intensity is suppose for example 110, so count will be equal to 110. So like that way you know that how to plot the histogram. You have studied that one in your first semester of digital image processing, okay, in that subject. So from that also you can extract the textural features. So how? Use the statistical moments of the gray label histogram of an image or region. Like for example, Z be the random variable denoting gray label, and let P Zi, probability of Zi, okay, and I is ranging from 0 to L minus 1. See that, because you are considering the intensity equal to, see, in case of gray label, this one gray label image, you know that L value is 256. So 256 maximum value will be equal to L minus 1, that is equal to 255, because you are starting from 0, so maximum value will be equal to 255. So be the corresponding histogram, and where L is the number of distinct gray labels. So L is the number of distinct gray labels. So how many distinct gray labels are there? There are 256 distinct gray labels. So starting from 0, it will be 255. So first feature from that one you can calculate is the mean feature. So once you have obtained the this one histogram, so calculate the mean of that histogram, so that can be used as a feature in the texture as a mean feature, right? So how to calculate that one? I equal to summation I equal to 0 to L minus 1 Zi into probability of Zi. So right. So then after, so this is one feature of which we can calculate from the histogram. Second feature is the nth moment of the shed about the mean. So nth moment, like as the okay, first moment, second moment, third moment, and then so on, so like that way. So this mu n is nothing. So if it is 1, it will be basically your mean itself. Okay. If it is 2, okay, we'll see. We can see that it will be second moment, and then if it is 3, it will be third moment, fourth moment, and so on. Now, what exactly second moment indicates, what exactly first moment indicates, and third moment indicates, so that we'll see in this one. So what you have to do basically, how to calculate the nth moment here. So from that histogram, I equal to 0 to L minus 1. So L is the basically distinct gray label, and then number of gray labels will be equal to 0 to N minus 1, and then Zi minus M rest to N. Now you are considering, like for example, this M minus N into P of Zi, right? So probability of Zi, that is nothing but the intensity of Z pixel, right? Now The second moment is given by this one, that is nothing but the standard deviation. So standard deviation, which is nothing but mu to z. So is particular importance. See, when you are considering the n is equal to here 2, right? So that is nothing but the second moment. Okay, if you are considering n is equal to 1, so that will result in this one. So that is nothing but your mean. When you are considering n is equal to 2 here basically this one, okay, z minus m raised to n. If you are considering that n is equal to 2 here, so that will result in the second moment, and second moment is nothing but your variance or standard deviation basically is a particular importance of in texture description, since it measures the gray level contrast that can be used to establish the description of the relative smoothness. So from that you can come to know what is the relative smoothness from the second moment. For example, if a measure of constant intensity R is equal to 1 upon 1 minus 1 upon 1 plus sigma square z, so that is nothing but your second moment. Okay, so you can basically measure the constant intensity. So it is nothing but the constant intensity. The standard deviation sigma is used frequently. Everybody knows in the histogram feature and so on. Then third moment. So if you consider the value of n is equal to 3, so here it will be 3, and then formula remains same because that is standard, and this measures basically the skewness of the histogram. Okay, whereas the fourth moment means if you consider the this n is equal to 4, this fourth moment is a measure of its relative flatness. So you can obtain the first moment, second moment, third moment, fourth moment, up to seventh moment. You can obtain the features from the histogram, and those features can be used as a textural features. So the fifth and higher order moments are not so easily related to the histogram shape, but they do provide further quantitative discrimination of the texture content, right? So from histogram also you can obtain various moment features, and then those features can be used to describe the texture, right? So another histogram features are like, for example, some other texture measures used on the histogram are uniformity. You can calculate the uniformity. So uniformity U is equal to given it is given by summation I equal to 0 to L minus 1 p square probability square of Zi. So U is maximum. See, if you when you this will be maximum for an image in which all gray levels are equal or maximally uniform. It's like, for example, if I consider image like 16 by 16 image, right? And then in that 16 by 16 image, 256 different pixels will be there, and then every pixel is having unique intensity value. Like, for example, one pixel is having intensity equal to 0, second pixel is having intensity equal to 1, third one 2, so like that way up to 255, right? So if I plot the histogram, so it will be just flat histogram because every intensity there are equal number of pixels, right? So it will be maximally flat or uniform histogram. So U is maximum here for an image in which all gray levels are equal or maximally uniform. So this is one of the measure for extracting the features, texture features, that is uniformity. Then average entropy, you can calculate the entropy from the this one. Once you calculate the probability of pixel intensities in the image, so entropy is given by minus because see that this value is generally log to the base 2 1 upon pz. So instead of 1 upon pz, if it is plus, you have to consider this as 1 upon pz. You are directly considering this as a log to the base 2 p of zi, then this value will be equal to minus, right? So this entropy, see, this is nothing but the knowledge, okay, information. Zi is nothing but the information. And so this part P of Zi is nothing but the information, and this is nothing but the entropy. So you know that entropy, this one, information will be maximum if probability is less. See, 1 upon P of Zi, 1 upon P of Zi is nothing but the information. So this will be maximum if probability is less. Means, see that if event is occurring at less interval of time, then that becomes information. Otherwise, if that event is happening every day, then that cannot be a news or that cannot be a information, something like that. So for information, this value 1 upon P of Zi, if it is maximum, then we can say that there is a maximum information. But if probability of Zi is more, then information will be less. So entropy is calculated based on the this one information and the probability of that pixel intensity. So how it is calculated? So summation over I equal to 0 to L minus 1 P of Zi, that is nothing probability of pixel having intensity Zi, and then log to the base 2 P of Zi. So in that way you can calculate the entropy. So entropy is a measure of variability and is 0 for the constant image. Means this value of E will be equal to 0 if the image is constant, right? For a constant image, otherwise it will be different. So you will get the variability of the image from the this one entropy, right? So you can calculate the histogram features, like for example, many features for smooth image. See that you can calculate. See that you can see from this one and these images. For smooth image, mean feature is less. Okay, for coarse image, mean feature is large, right? For regular image, okay, it is in between smooth and coarse. Similarly, standard deviation for smooth image, okay, standard deviation is very less. Coarse image, standard deviation is large, and for regular image, it is in between this one. So see that means what you can see that once you calculate the standard deviation and mean of the image, you can tell whether that image is smooth image or whether it is a coarse image or coarse texture or regular texture. So like that way, from all those things, see that these are the features which are extracted for smooth image, like this mean, standard deviation, are normalized, the third moment, uniformity, and entropy. For coarse image also it is like this. For regular image it is also like this. So from these values you can estimate what will be what kind of image will be there, whether it is a smooth image or coarse image or regular image, and so on, right? Then histogram and features, like for example, measure of the texture based on the histogram suffers from the limitation that they carry no information regarding the relative position of the pixel, because you are considering the entire image, okay, and then you don't know, you are losing the relative information about the pixel with respect to each other. So one way to bring this type of information into texture analysis process is to consider not only the distribution of intensities but also the position of the pixel. Means here what you are doing, you are considering only the intensities. You are not talking about where is the position or location of that intensity and so on. But to get more information or to get the meaningful textural features, you have to consider that also. Means intensity as well as its location. So one way to bring this type of information into the texture analysis process is to consider not only the distribution of the intensities but also the position of the pixel with equal or nearly equal intensity values. So that is okay. Now the next feature, that is co-occurrence matrix. So in our next lecture we'll continue this one. So today we'll stop here. Thank you very much.